Okay, Abel's theorem tells you that if you have a homogeneous linear equation, and not necessarily with constant coefficients, because of course, if you have constant coefficients, everything's pretty straightforward. Your Wronskian turns out to be simpler. But anyhow, you have this, then the Wronskian at any point t is equal to the Wronskian at t naught times e to the big P of t. Okay? That's the last day of class. So all I want you to be able to do is use the thing. Okay? We won't have time to prove it. We won't have time to extend it to Abel's theorem for systems or to the more advanced things that I like to do with systems, okay? But you have basic systems now. Okay, so Abel's theorem tells us that W of t equals W of t naught e to the P of t. So let's apply it, okay?
In my head, I'm still doing things in the same order still. All right, so that's a 9-1 question. All right, so basically here's what's going on.
Well, P of t is an antiderivative of your t function, which is t. I'm just going to use t squared over 2. Okay, so now we know W of t equals W of t naught. E actually, when I wrote this down, I didn't quite write it down right. Okay? You do have the P of t here. And I like to use that notation. So, yeah, okay, it works. It's the integral from t naught to t. And then maybe we need a dummy variable in here, so I'll make it time. Okay?
Okay.
So it's from t naught to t because t naught has to be part of this. Carelessly didn't write that down. Wasn't thinking. Till I got here, and I said, wait a minute, yeah, we need that. Okay, so you got W of t equals W of t naught times, and it's okay, it's from t naught to t, so that's t squared minus t naught squared. T squared over 2 minus t naught squared over 2. Okay? So it's e to the t squared minus t naught squared over 2. Well, among other things, this equals W of 1 e to the t squared minus 1 over 2.
And then we're going to multiply both sides by n to clear the fraction.
I just substituted 1 for t naught.
Yeah.
So if I know the Wronskian at any point, I can use that point. Okay? So this is equal to 4e to the t squared minus 1 over 2. So there's your Wronskian.
Back to your original question. Because it comes from your
Okay?
confidence interval. It comes from the margin of error confidence intervals.
Now if you have one solution in the Wronskian, you could often be able to find the other solution. But we're not going to do that. Okay? The book doesn't even do it. And I'm certainly not going to ask you to take that chunk between now and the final, okay? So you have this. So what the problem asks you to do is find W of 2.
One way to do a hypothesis test is with confidence intervals. You can build a confidence interval to do a hypothesis test that only
don't have a lot of room, I'll just do it here.
Confident intervals do not work for non-field tests. That's why I don't teach using confidence intervals for hypothesis tests, because that's the only time they work. Does that make sense? That's why when you're doing those p-values or two-tail tests, p-value is actually the sum of the area in both angles.
Gotta be 4 e to the 3 halves.
For one-tail test, it's only the area in the one tail.
I mean, all we're doing is, we're trying to find W of t. We have a formula for W of t. We plug in, we want to find W of 2, we plug that in for t.
No, that's not so much
Okay.
about, if I think I understand what you're talking about. That's like.
Now the connection here is simply this integral of the little p of t ought to connect you. That should be fairly easy to remember, because one of the very first things we did was the integrating factor and all that stuff. You know, it's much like the integrating factor you would use for a first order equation. Okay?
So how do you use this to solve an equation?
You know, you use it to build solutions from known information, even if you can't solve the equation. Or, well, your book doesn't do examples. I don't feel it'd be a good idea for me to try to make one up on the spot.
So
Okay.
why would it be relevant that W of 2 is 4e to the 3?
Well, why would it be relevant?
If we don't know what...
Yeah, it's a good question. We don't have time to really do it. Okay?
Okay.
Because it gets a little involved. Okay? And your book doesn't really address it, so you don't have a good resource to help you understand the answer to the question. Okay, also I'd probably stumble through it right now. Okay, I'd probably make something up and then find after 16 steps that there's a flaw in my example.
Yeah.
Okay? So I give you very general hand waving stuff that you're not going to remember, not going to do you any good. Okay? Yeah, I was thinking I should have looked at the book to see what kind of examples they did. I was assuming they did an example where they did something with it. I don't see where they do. There are 4 problems at the end of the section, and they're all pretty much of this nature. Okay? One of them's a little trickier than this, but they're all very similar.